So this is the sixth FRQ of the Unit 11 project. So let's get into it. For this, we're going to need to know capacitance equation, and that's the dielectric constant times permittivity of free space times area over distance. And then our time constant, it's going to be C. And then our half voltage time, 1/2. At that time, our VC will equal 1/2 Vmax. And our equation for charging is VC equals Vmax times 1 minus to the negative T over RC. And then for the last thing we're going to need to know is that parallel capacitor, 1 plus C2. And then, so now we have everything we need to solve this. So, what we're going to do is, using that equation for charging to solve this, we can write that at half, that's going to be Vmax, and the only thing is we're going to have to plug to the negative T, but at that half over RC. So now we're going to plug in 6 for that. So we're going to have 3 minus E T 1/2 over RC. And then that would mean we get 1/2 equals 1 minus T 1/2 over RC. And we're solving for C, so that should okay. So then it'd be E to the negative T 1/2 over RC. And then that would just equal 1/2. And then we're going to have to take the natural log of both sides to cancel out that E. And then we're going to, so then we get ln okay, so ln of 1/2, so we would get, sorry, my algebra today is not the best. They're rusty from break. And then ln of 1/2 would be the same as ln of 1 minus ln of 2. and ln of 1 is just 0. That would cancel, so we have two negatives. And it would just, they'd cancel, so we'd be left with T1/2 over RC equals ln2, and then we could just rewrite it as C equals T1/2 over R ln2. That's our answer to A. So now we're gonna plot the data points, plot the experiment value of the capacitance C. Okay, so this would just be plotting data. That's pretty straightforward. Our x-axis 0.05, so we could just do it in 0.05s. One. Two, 5, and then for our C, so at 1.2, we start at 1, but by 5. It does the zoom in thing. And then .5, and then be 0.05, 1.27, something like that. 0.1, 1.82, something like that. 0.15, 2.16. That. 0.2, 2.54. And then 0.25, 3.17 will be like there. And then line best fit. It's not gonna be great because I'm on a computer, but like that. So that's our job. And then we label the axis. So capacitance on the y, x on and then our distance on the x-axis. Okay, and then now part C, our slope capacitor. Our slope. So the system is two capacitors in parallel, one with air and one with plastic. And that would mean that seconds. Two. I'm just rereading this. Two capacitor. One okay. I got it. so it would be our area of plastic. That's gonna be, let's call it SX. And then our area of air, that's gonna be S minus X. So then our capacitance of the plastic, that's C air is gonna be, there's no dielectric there, but our area is different. That's going to be D over D. And then our C total, since they're parallel, we're going to be able to add these. So, sorry. So then that would mean we could factor out epsilon naught over D kx plus x minus x. And then, oh, okay. So then that equals epsilon naught over D oh, this is epsilon naught S. Sorry. Epsilon naught S over D times S plus, and then factor out this X. So K minus 1. And that's our answer. And now calculating the dielectric constant, that would mean okay, so calculating the slope, which I have my calculator, that would be 9.5, so based on the graph, and then that equals S D one, and our y-intercept is epsilon D, that would be 0.8, and then we'd have our, to calculate K, we could have our M over B, that would be 9.5 over 0.8 for 0.8. And then that would equal K minus 1 over 0.3. And then solving for that, we get K equals 4.56. And then for, oh, well, I'm out of time, so we're going to have to do a part 2 to this.